Welcome to Calculus. Today we are going to explore a fascinating topic called particular integrals. If you have ever wondered how a suspension bridge reacts to rhythmic wind or how an electrical circuit responds to a battery, you are in the right place. We will build your understanding from the ground up, so do not worry if this is completely new to you. Let us dive in and discover how mathematics describes forced behavior in the real world. To start, imagine you are riding a bicycle on a completely flat road. If you stop pedaling, the bike will eventually coast to a stop due to friction. In mathematics, this natural, unforced coasting behavior is called the complementary function. Now, imagine you start pedaling continuously with a steady, rhythmic push. The bike's new motion is a direct result of your active pedaling. This forced, driven behavior is exactly what a particular integral represents in calculus. It is the specific part of a system's mathematical solution that responds directly to an outside force. Unlike the natural response, which depends on how you started, the particular integral contains absolutely no arbitrary constants. It perfectly balances the external force applied to the system. Now that we understand what a particular integral is conceptually, let us look at how it fits into the bigger picture. The formula you see here represents the complete general solution to a differential equation. The variable y represents the total behavior of the system over time or space. This total behavior is made of two parts. First, y sub c is the complementary function, which describes the natural, unforced behavior of the system when no external forces are acting on it. Second, y sub p is the particular integral, which is the specific response generated entirely by the external forcing function. If the external force increases or changes shape, the particular integral will change to match it, while the natural response remains fundamentally the same. Together, they give the full picture. This formula we just saw leads us to an important question. How do we actually find this forced response? We often use a technique called the method of undetermined coefficients. This relies on a beautiful and simple idea known as the pattern matching principle. The core idea is that the forced response of a system usually looks exactly like the force itself, plus its derivatives. Think about pushing a swing. If you push it with a smooth sine wave motion, the swing will eventually move in a smooth sine wave motion. Therefore, if our forcing function is an exponential function, we logically guess that our particular integral will also be an exponential function. We set up a trial solution that mimics the exact shape of the external force, leaving the specific numerical multipliers as unknown variables to be solved. Before we move on to an example, let us compare our tools. Students often wonder when to use the method of undetermined coefficients and when to use a more advanced technique called variation of parameters. Think of undetermined coefficients as a specialized, highly efficient tool. It is incredibly fast, but only works for simple forcing functions like polynomials, exponentials, sines, and cosines. It avoids integration entirely, relying only on basic algebra and derivatives. On the other hand, variation of parameters is like a universal master key that works for absolutely any forcing function, including complex ones like secant or tangent functions. However, its computational steps require evaluating complex integrals, which can be very difficult and time-consuming. You should always prefer undetermined coefficients when the force is simple. Now that we have our method, let us see this with a concrete example. We are given a second-order differential equation where the external forcing function on the right side is an exponential growth function, e to the power of 4x. We need to find the specific mathematical response to this exact force. Because the right-hand side is a simple exponential, we use the method of undetermined coefficients. Following the pattern matching principle, we guess a trial solution that is a constant multiple of this exponential function. We call this y sub p equals a times e to the power of 4x, where a is our unknown constant. To see if this guess works, we take its first derivative, bringing the 4 down, and then its second derivative, giving us 16a times the exponential. Continuing with our example, we now substitute our expressions for the trial solution and its derivatives directly into the left side of the original differential equation. This substitution is the core mechanical step of the entire process, transforming our differential equation into a simple algebraic equation. We replace every term carefully. Next, we simplify the left side by performing the basic multiplication inside the parentheses, distributing the -3 to get -12. Finally, we combine the like terms on the left side. 16 minus 12 is 4, and 4 plus 2 gives us a final coefficient of 6. This single term, 6a times the exponential, represents the entire left side of our differential equation, perfectly balanced against the external force on the right. Building on our simplified equation, we notice that the exponential term is present on both sides. Because an exponential function is never equal to 0, it is perfectly safe to divide both sides by it. This isolates our unknown constant, leaving us with a very simple linear equation. 6a equals 1. Dividing both sides by 6 gives us the final value for our unknown coefficient, which is 1/6. This specific number is the exact value required to balance the external force. We substitute this numerical value back into our original trial solution. This gives us the final, complete, particular integral for the system. There are no arbitrary constants left. It is a single, exact function that perfectly satisfies the first condition of our system. So, we have found our particular integral. This brings us to an essential step, verifying that our answer actually satisfies the original equation. This acts as a mathematical proof of our result. We start by finding the derivatives of our final answer. The first derivative is 4/6 times the exponential, and the second derivative is 16/6 times the exponential. We plug these exact values back into the left side of the original differential equation. When we multiply the terms out, we get 16/6 minus 12/6 plus 2/6, all multiplied by the exponential. Adding these fractions together simplifies exactly to 6/6, which is just 1. This leaves us with exactly the exponential function, which perfectly matches the right-hand side. We have proven our solution is absolutely correct. Now that we have verified a basic case, let us explore a more complex scenario. Sometimes the external forcing function perfectly matches the natural, unforced behavior of the system. In physics, this is called resonance. Like when an opera singer hits the exact natural frequency of a wine glass, causing it to shatter. Mathematically, resonance happens when our forcing function is already a part of the complementary function. If we just guess the standard trial solution, it will collapse to 0 when plugged into the equation, giving us no useful information. To fix this, we must multiply our trial solution by the independent variable. But if the forcing function is a polynomial multiplied by an exponential, we face a severe case of resonance that requires multiplying our guess by even higher powers of the variable. Building on the concept of resonance, let us solve a problem where resonance occurs alongside a polynomial force. We are looking at a system where the forcing function is x times e to the power of x. First, we identify the natural behavior. The characteristic equation has repeated roots of 1, so the complementary function already contains the exponential of x and x times the exponential of x. Because our forcing function completely overlaps with this natural behavior, a standard guess will vanish. To overcome this double root resonance, we take our standard polynomial guess, which is ax plus b, and multiply the entire thing by the independent variable squared. Distributing this gives us our modified trial solution, ax cubed plus bx squared, all times the exponential. This ensures our guess is mathematically independent from the natural response. Continuing with our resonance system, we must find the first derivative of this trial solution using the product rule. We take the derivative of the polynomial part times the exponential plus the original polynomial part times the derivative of the exponential. This generates several new terms that we must keep track of. To make the next derivative easier to calculate, we group the terms by their powers of the variable. We gather the cubed terms, the squared terms, and the linear terms together inside the parentheses. Keeping the polynomial organized like this prevents massive confusion later. This is a crucial algebraic habit when dealing with complex forcing functions. Following our organized first derivative, we take the second derivative, applying the product rule one more time. The process is exactly the same, just with slightly larger coefficients. We differentiate the polynomial part first, then add the original polynomial part. We group the terms again by their degree to get a clean expression for the second derivative. Now, we substitute our function, its first derivative, and its second derivative back into the original differential equation. When we carefully combine all these terms, subtracting twice the first derivative and adding the original function, a beautiful mathematical cancellation happens. All the terms containing the variable cubed and squared completely cancel out to zero. This massive collapse is the hallmark of the resonance method working correctly, leaving us with only the lower degree terms equal to the forcing function. Building on that massive cancellation, we can divide both sides by the exponential function, since it is never zero. This leaves us with a simple polynomial equality. 6ax plus 2b equals x. We are now just comparing a straight line on the left to a straight line on the right. By comparing the coefficients, we set up a simple system of equations. The coefficient of the variable on the left, 6a, must equal the coefficient on the right, which is 1. The constant term on the left, 2b, must equal the constant on the right, which is 0. Solving these gives a equals 1/6 and b equals 0. Substituting these back into our trial solution, the zero term disappears, giving us our final particular integral. This clean mathematical function perfectly balances the highly resonant system. So, we have proven how to handle resonance. This brings us to verifying our complex result to ensure it is absolutely correct. We take our final answer, 1/6 x cubed times the exponential, and find its derivatives. The first derivative uses the product rule to give 1/2 x squared plus 1/6 x cubed all times the exponential. The second derivative simplifies to x plus x squared plus 1/6 x cubed times the exponential. When we plug these exact expressions back into the left side of the original differential equation, we carefully distribute the -2. The x cubed terms perfectly cancel out. The x squared terms perfectly cancel out. We are left with exactly x times the exponential, which perfectly matches our external forcing function. The mathematical reasoning holds up and our resonant solution is verified. Now that we have used this formula and verified it, let us understand why this matters outside the classroom. Understanding particular integrals is absolutely critical for engineers and physicists who design real-world systems. Whenever you build a suspension bridge that must withstand rhythmic wind gusts or design an electrical circuit driven by an alternating current battery, you are dealing with forced systems. The particular integral tells you exactly how the bridge will sway or how the current will flow in response to that specific external force. If engineers only calculated the natural, unforced response, they would completely miss how the system behaves when actually turned on and put to work. Without calculating the particular integral, we could not predict resonance, meaning bridges could collapse and circuits could overheat and explode. Let us look at a visual representation of everything we have discussed. On this graph, the horizontal axis represents time and the vertical axis represents the displacement or behavior of the system. Notice the dashed line starting on the left. This is the complementary function or the transient response. It oscillates initially but quickly decays and fades away to zero due to natural friction. Now look at the solid, continuous wave. This is the particular integral or the steady-state response. It is a uniform, rhythmic wave that persists indefinitely as long as the external force is applied. The actual behavior of the system is the sum of both. Initially, the motion is messy as the natural and forced responses mix, but eventually, the system settles entirely into the steady, driven rhythm of the particular integral. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the particular integral is the exact mathematical translation of how a system responds to an external push or pull, containing no arbitrary constants. Second, we learned that the method of undetermined coefficients is a powerful pattern matching tool for finding this response to simple forces. Third, we saw that when the external force matches the system's natural behavior, resonance occurs, requiring us to modify our trial solutions by multiplying by the independent variable. Finally, always remember to verify your solution by plugging it back into the original equation. You have now mastered the mathematical bridge between theoretical design and practical driven reality. Great job!